if I hope I'm not hopefully in a hurry, but if I'm in a hurry and you are taking screenshots, let me know that you are doing some screenshots so that
Yes.
you don't miss any concept. All right. So basically, heat is a form of energy that
Mm-hmm.
can affect matter, and the basic, well, at least apart from depreciation, the basic thing that heat can do to matter is to make it change its state. Okay. And by state, we mean solid, liquid, and gas. Okay. So those are the three main states that we know: solid, liquid, and gas. So let's see how that happens. Now, it's very important to understand that heat and temperature are not the same thing. Okay, so heat is a form of energy, while temperature is simply a measure of how much heat is, or how much heat is in something. Okay, so remember that
Mm-hmm.
temperature is just a measure. Heat is the energy, is what is, is a form of energy, while temperature is just a measure of how much heat is in, something, a substance. So you can see this basic definition for temperature is, it tells us how hot or cold something is. So that's why basically, if you want to measure the temperature of something, your best bet is to use a thermometer, right? It just a measure. Always remember that it's a measure. It's not heat. And you can even see from the unit for temperature. What are the units for temperature that you know?
Degrees Celsius,
Degrees Celsius. What other unit do you know?
Fahrenheit.
Fahrenheit. Good. Okay. Are you aware of Kelvin?
No.
Okay. Okay. All right. No problem. It's also a unit of for heat. Kelvin. However, I think most books might not mention it, but
Mm-hmm.
I think they call it absolute temperature. So that's basically on, maybe for you probably get to know about that later. But
Okay.
just know that there's a unit like that. All right. While the unit for heat is a form of energy, and most forms of energy, and in fact, I would dare say all of them usually have the unit of joule. Okay, joules. I think that was named after a scientist whose name is also joules. Okay, for as a unit of what? Energy. So anything that's energy, whether it's heat energy, sound energy, what other forms of energy do you have? Light is also, can also have a form of energy. What? Their units always go hang around that joules. Okay, so whether you have joules, kilojoules, or whatever, just remember that the unit of heat as a form of energy is also what? In joules. Okay, so this is the basic concept. When temperature increases, particles move faster. Okay. And what's the implication? Particles move faster. The implication is that particles were already in motion before, the temperature increased. And temperature increasing means what? The amount of heat energy in that substance is also what? Increasing. So let's imagine you have what does it look like? It's in this picture, water, right? Um, it looks stable, it's at room temperature, but as soon as you apply heat to it, what happens? After a while, you start seeing bubbles, right? Okay, so it's showing that the temperature is increasing. Okay, and that temperature, again, remember, the temperature is simply a measure of how much heat. It's not exactly the amount of heat, but it's a measure of how much heat. In fact, some books will say the average measure, of the heat inside the substance. So that's the temperature. So when the temperature increases, that shows us that heat is being applied. The particles which were already in motion will tend to move faster. And the aim is that as they're moving faster, the forces holding them will do what? At a point, will not be strong enough to keep them, together. And that's what happens when a state change occurs. So just have that in mind. So you can see that another name for heat energy is what? Thermal energy. Okay. Particles move faster. Sorry, I'm doing my best not to slide too fast. Okay. All right. Of course, the opposite happens when temperature decreases. Particles are slower. All right. So this is what happens at a point when a solid is heated enough. Okay, it does what? It melts into a liquid. So melting is what? A state change. So I think that's, let me see. That is one effect of temperature. Remember one effect of heat, sorry. Remember how we started that the primary thing that heat does to matter is what? A change, it affects matter by, of course, a change in state, okay? So this is what we're referring to. So now remember this, when you start heating, you can see that picture there that has 3 blocks of ice, right? You can see that ice will still remain ice, but it will gradually be turning to water until, but before it turns to water, at the initial stage, ice can still stay as ice, and it will not look as if anything is happening until what? It gets to the point where what happens? All the heat it's taking in is for what? Changing it from what? Solid to liquid. But now that point where it looks as if, oh, nothing is happening, it's absorbing heat. It's just that at that point, the heat that it's absorbing is only changing its temperature. Okay, so remember that heat can do what? Change the temperature of a substance. And at the same time, after a while, that heat will no longer just change the temperature. It will change the state of that substance. So it goes from what? If it was a solid, it will go from what? Solid to liquid. If it was already in liquid form, it will go from what? Liquid to gas. Now, of course, you know that there are some exceptions. You've already learned about sublimation, where a solid can go straight from solid to gas. Okay, and there are few substances that exhibit that behavior. Okay, so let's move to the next slide. This one talks about a liquid. When a liquid is heated sufficiently enough, it becomes what? A gas. Now, one thing I must say here is this. Just like I said about ice, it will look as if nothing is happening to it. You are heating it, nothing is happening. But at a point, it does what? It now starts changing from, or starts melting, okay? Now, it's been observed that when ice starts melting, if you are using a thermometer to check its temperature, it will not change at the point it starts melting. So what does that tell you? Remember, the thermometer is simply telling you how much heat is in the particles of a substance, isn't it? So the molecules, I think it's safe for us to say molecules. So the molecules of the water, the ice, at that point, they are no more just absorbing heat to be moving faster. They are now absorbing heat. The heat that is absorbing now is called latent heat, and the word latent simply means hidden heat. That heat is what will make it to do what? Break the bonds that are holding to called ice. Once that happens, you will notice the thermometer will no longer increase. It will stay constant until what happens? All the ice has become what? Water. At that point, guess what will happen? The temperature now starts rising again. Okay, so it's a basic concept, but I'm sure you would understand it, maybe from experiments or just or just basic experience. Okay, so remember that when you just remember this: when you put a pot of water on fire or on the gas to boil, you notice it will take a while before it starts boiling, right?
Mm-hmm.
Take a while. Now,
Yeah.
that between when you put it on the gas and when it starts boiling, what's happening? The temperature is doing what? Increasing.
Rising.
At that point, it's simply absorbing the heat energy from the gas burner. It's absorbing the heat energy. Okay. And so the temperature, the thermometer is simply doing what? Is simply doing what? Is simply increasing. The temperature is simply increasing. Okay.
Mm-hmm.
But the water has not become gas. At the point the water starts boiling, that's going to be roughly 100 degrees Celsius. If it's pure water, right? 100 degrees Celsius. At that point, the thermometer will stay constant. Why? Because any heat is absorbing from the burner is no longer for what? Just increasing the temperature. It's for what? Changing the water from liquid to what? Gas. Okay? So always remember that heat does two things. It increases the temperature of the substance, and at a point when it's sufficiently, hot enough, it now gets to the point of changing the state of the substance. So two things that heat will do for you. So in this case, boiling water becomes steam, and that's what looks like smoke right there. If you leave it for a while, all that stuff that looks like smoke there is actually the water escaping into the atmosphere. All the water in the pot will disappear. Okay, so, all right. How does this phenomenon happen? Where it looks like something that you took out of the freezer or the refrigerator. If you look at the body of maybe a bottle of Coke, a bottle of soft drink, or a bottle of water, you just brought it out of the freezer, right? And then after a while, you start seeing droplets of water around it. Simple. Now, yes, I hope I'm not rushing this. Because those concepts that your mom dropped there, they're kind of mixed together. So maybe I'll be mentioning them. So now, how does energy? I think there's a what they call that thing? A theorem. Yes, it's safe to call it a theorem. Yeah, or laws of energy. Energy can neither be created nor destroyed. Okay, so that's one of the laws, and the only thing that can happen is what? It can change from one form to another. Okay, so remember that energy can neither be created nor destroyed, but it can only change from one form to another. So changing it from one form to another, in this case also, heat energy can flow from one substance to another. So usually, if something is hot, right, it's because energy is flowing into it. Okay, so heat energy is flowing into it. If it gets cold, then heat energy is leaving it. Okay, so heat energy will usually flow from something that is hot to something that is not so hot. Okay, did you get that?
Yeah.
So that's the reason for this phenomenon where it looks like water droplets are forming on a cold glass of water, a cold glass of a drink or something. Simple. In the air around that glass, there's water vapor, right? But you don't see it. Guess what happens? Those water vapor, as invisible as they are gas. At that point, they are gas. But now, what happens is that remember that heat would flow from something that is hotter to something that is not so hot. Okay, so maybe we should put it that way. So remember that for gas to become liquid. So now let's do as if we're going, okay, so let's start forward. For solid to become liquid, it needs heat, isn't it? Okay, so let's work from that way upward. For liquid to become gas, it needs heat. It absorbs heat, isn't it? Now, if we want to go backwards, for gas to go back to liquid form, what should happen? It won't absorb heat. Heat will be taken from it. In other words, its temperature will be reduced. Did you get that?
Yes.
Okay, so that's what happened to those water droplets around the cup or around this cup in this picture. Simply put, heat was absorbed from them. And that is why they now became what? Liquid that you could see. Remember, they were when you couldn't see them, the first time you probably brought out this glass of cold, chilled water and kept on that table. Okay, they were gas. You couldn't see them. But after a while, they gave up their heat and became what? Liquid. Okay, so that's the reason why they are now visible and staying around that glass of water. Now, after a while, remember, the heat is absorbed from them. After a while, that cup of water would no longer be cold. And I'm sure you know what's happening, right? It's absorbing heat from the surrounding. So when it keeps on absorbing that heat from the surrounding, the water is no longer cold anymore. Did you get that? Okay. All right. So just thought I should explain that phenomenon. It may just be good for you to understand it. So, of course, when a liquid is continually cooled, in other words, heat is absorbed from it, heat is taken out from it, it becomes what? A solid. And that's simply what happens when you put water in a refrigerator or in the freezer. Okay, so water turns into what? Ice. Okay. All right. Okay, so these were the things I told you about. Temperature is measured using these units: Celsius, Fahrenheit, and Kelvin. Okay. Okay, so there was this older unit. I don't know if you guys are told about it. I think that was replaced by Celsius. Have you heard of it? Centigrade.
I've heard of it before.
Okay, all right. So I
Centigrade.
guess yes. They probably didn't mention it to you guys because, well, it's an older unit. I think it got phased out and was replaced by Celsius. But yeah, essentially it's also a unit, but I guess you don't need to bother with that, right? Just understand that there was a unit like that and it's old. It's no longer in use. Okay. Yes. All right. So okay, so these are just some questions that you may want to use to test yourself. Let me revisit what your mom put on the on the group so that make sure that we have okay. So temperature change. Let's see. Next temperature change. Okay. Transferring energy. Okay. 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 All right. Okay, so basically this is so these are some questions. We'll just go through this, then I'll open the material I have for that should probably address transferring of energy. Okay, so what would be the answer to this question? You place an ice cube under the sun. After a few minutes, it turns into water.
Is it melting?
Yes, it's melting. Yes. Okay. All right. Okay. How about this one?
Opening the hosting coming out. Things up into the water. Is it liquid to gas?
Yes, exactly. Liquid to gas. Yes. Okay. Okay, no, don't worry about this one. This one is basically location based, but I don't think they would ask you guys that. How about this one?
If a thermometer shows a temperature of 0 degrees, what does this mean? Does it mean water is freezing?
Yes, water is freezing. Okay. How about this one?
It's just which is a bit similar clone loss of juice. What caused the gas to turn into liquid? Is it cooling?
Yes, it's cooling. That was the concept that we just described. Okay. Okay, I think this. Okay, all right. So these are the answers. Okay. So yes. All right. So let me quickly get out the material for transfer of energy. That would have to do with conduction, transfer of energy. Energy source is. Okay, so I'm specifying my search around heat energy, right? Okay. Because if we okay. Okay. All right, I'll be sharing my screen now. So were you doing any screenshots while I was explaining?
No, I was writing it down in my book.
Okay, all right. Okay. Okay, so can you see my screen now?
Yeah.
Okay, all right. Okay. So this is basically the understanding of what heat energy is, the total kinetic energy. Okay, so remember, temperature is the average, okay? While the total energy, the heat energy itself is the the total kinetic energy of the atoms or molecules in a body. And while temperature is simply a measure of the average kinetic energy, which is like what a measure of what is in one molecule of that substance. So it's just a measure. Always remember that. While heat energy is the total kinetic energy, and kinetic always has to do with what? Movement. Okay. In terms of stuff, something that's moving. Okay, kinetic energy. All right. So the next thing is what I mentioned back then. This energy, the energy is transit or moves from a high temperature object to a lower temperature object. That's the reason why the water droplets were invisible as a gas. They are at a higher temperature than the water inside the cup, which is at a lower temperature. So heat will leave from them and enter that water that is in the cup, leaving them with no choice than to do what? Turn into water droplets, which you can now see on the outside of the cup or the bottle of soft drink or whatever drink it is or water. The amount of thermal energy transferred is the amount of heat that flowed. Okay, so this is with an assumption that no heat is lost to the environment at all. Okay, all the heat that was transferred was what absorbed. So that's the assumption. Okay, but of course, some other people may feel otherwise. That something else may have happened in the course of that. Thermal energy is transferred in three different ways, like I mentioned: conduction, convection, and radiation. So let's quickly look at these.
I'm writing it down.
Sorry?
Can I quickly write it down?
Oh, okay, sure. Why not? Go ahead. Yes.
Mm.
Okay, are you done?
Almost.
Okay.
Okay,
All
I'm
right.
done.
Okay. All right. So, two things, or should I say basically one, or maybe we should just consider the concept. Conduction and convection, they need mediums, or let me use the right word, media. Okay, so that's the plural for medium. Okay, so what does that mean? It's either a solid or a liquid, and usually conduction is via a solid. Okay, so look at the basic this thing. It's the process by which thermal energy, you know by now that thermal is another word for heat, is transmitted through a medium from one particle to another. For example, you place one end of an iron rod in fire. Before you know, did you say something?
No, no, no.
Okay. Before you know it, the other end uh, also heats up. Okay, so that's basically what's happening there. Um, of course, I think it's good to remind ourselves that some objects are better conductors of heat than others, right?
Mm-hmm.
Well, we learned about metals the other time, and metals are good conductors of both heat and electricity. So
Wait,
that's
shall I write the conduction thing?
okay. Yes, yes, yes.
Because he wasn't compared to the Black Plague, but the thing that people don't understand is the Black Plague, if that was to happen now, the Black Plague is like a cold. The reason why it was so bad is because we didn't have what we have now. It's not the same thing compared to the Black Plague even happening now. It's not the same thing. The Black Plague was basically, no offense, it was practically a flu. The reason why I didn't get treated was because we didn't have the necessity to treat it. But if you want to say, oh, something compared to a Black Plague, at least say something like Tennessee or something, then fair enough in that. But a cold is not going to turn you into the Black Plague, really. Like, you know what I mean? Like,
But as you see, like we're seeing the coverage I get, it's because kids just want something to happen. The youngins just want something to happen. Like they actually just want something to happen. There's always top niggas in the world that just want shit to happen. That's not anything. That as much as even if lockdown is probably quite much right, because that means I'm getting 60. But that's not the point. I don't want that. I don't care that they need shit out in front of it. But that actually is that genuine unfollow.
Okay, are you done?
Um,
Almost.
mm-hmm.
sounds. I think
Please. Okay, I'm done.
Okay. All right. Okay, so let's move on. So take note of these things. It's transmitted through a medium from one particle to another. So this is the explanation for how it happens, right? Uh, you can see the molecules in that are at the place where the temperature, the heat is being applied are red, while the ones that are, at the part where the heat is flowing to are blue. Okay, so that's usually the color coding. Red is hot, blue is not so hot or cold at a point. But if that continues, eventually all of them will be red hot. Okay, so now that we have that at the back of our minds, let's look at what's really happening. When one end of the rod is heated, the molecules gain energy and do what? Vibrate faster. Always remember this. The molecules were already moving. It's just that they were not moving that fast. Now they are getting hotter and they are moving faster. So this will cause them to collide with their less energetic neighbors, and that would now do what? Cause energy to be transferred to the neighboring molecules, which in turn do what? Gain kinetic energy. Remember, kinetic energy is energy in motion, okay? Energy that happens as a result of motion. Don't forget that. So what happens next is that, sorry, 1 minute. What happens next is that uh, this continues until the cold end reaches the same temperature as the hot end. This is just an explanation. Do you want to take notes of this too? Or it's something that you feel you'd be good with?
Okay, let me just take it.
All right. Because sometimes I think understanding how conduction happens and all this heat transfer happens is very, very essential. The details as to what's happening there inside the substance, whether it's a solid or a liquid.
Call. Got 10 minutes and I think one more to answer. Which game?
Don't say the words.
I was I wasn't going to do it. I thought it was rude.
Acelele, acelele. Acelele, acelele. Need to go. What was done? Right. Or actually, it's I'm calling it to be
Okay, can we move on now?
Uh, I'm on
Okay,
the last
okay,
paragraph.
okay, the last one. Okay, no problem.
Okay, I'm done.
Okay, excellent. All right, so let's move on to the next um, um, major heat change. Okay, so some things to just note. Conduction in metals is far better than other solids as it takes place through uh, the vibrating molecules as well as free electrons in metals. So this is alluding to the fact that metals are better conductors.
Wait,
Okay.
can you repeat that sentence again? The conduction in metals.
Okay. The conduction of thermal energy in metals is far better than in other solids, as conduction takes place through vibrating molecules as well as free electrons in metals. Okay.
Mm-hmm.
So that's the so now what this statement simply would mean is that conduction will happen whether it's a metal or a non-metal. However, um, it's better and faster in metals. Okay, so that's the difference. Did you get that?
Mm-hmm.
Okay.
Mm.
All right.
Uh,
So I think um, that's it. So okay. So let's see. Okay, this is just an experiment comparing four good thermal conductors. So basically, there's boiling water, and then different solids are inserted into or have already been inserted into through holes, touching the boiling water. So the one that would show the faster melting of that wax, would be the one that conducts better. So wax is if you notice at the tip, wax is placed at the tip, and that's like your candle. Okay. So there are examples of good conductors: gold, silver, copper, iron, brass, aluminum. Poor conductors: glass, stone, water, plastics, wood, polystyrene, foam, wool, and fiberglass.
can
Okay.
I please, can I write that table?
Yes, please. You can write that. Examples of good conductors and poor conductors, which could also be classed as insulators. Okay. Are you almost done?
Yes.
Okay. So I want to see if we can do convection and let me see. I'm looking at how much power I have left, except a miracle happens now. Convection.
Didn't really work.
Okay, are you done?
No.
Okay.
I'm done.
Okay, all right, good. Okay, so I'm skipping some non-essentials so that we can focus on the main thing. Okay, so I'm going straight to convection. All right, so now I'm sure by now you'll be able to see the difference between conduction and convection. So liquids and gases are poor thermal conductors. But if they are free to circulate, that means if they can move, of course, then they can carry thermal energy from one place to another pretty quickly. Okay, so that's where convection comes in. It's the process by which thermal energy is transmitted from one place to another by the movement of heated particles of a gas or a liquid. Take note, we don't discuss convection in solids, okay? It's usually either a gas or what? A liquid, okay? So once we have understood that fact, then we rest our case. Now, of course, we can see this is just a reminder that molecules in solids only vibrate about their fixed positions. They don't move like move per se. Okay. While in convection, we have the atoms or molecules that move from one place to another, and that's how thermal energy um, um, can now move. Okay, can now actually happen or be transferred. Okay, so let's remember that part.
Mhm.
Okay. So did you get that?
Mhm.
Okay, so I know you probably are thinking of taking notes. Are you already writing?
Yeah.
Okay, all right.
I don't think I think our boss don't do.
Okay, so while you're writing, there are some things you
I want to
can
find out what we
think
got.
about. I can leave you with. You know the part of a car engine called the radiator, right?
Pardon?
The part of a car engine called the radiator. You know that part of the car engine, right?
No.
Okay, so that's maybe I don't know if you've been. I think definitely you have an idea now. When you open the hood of a car, okay, of course, a typical car, right? There's this part where you can put water in it, right? To help that water helps to cool the engine.
Mm-hmm.
You have an idea of what I'm talking about now.
Yeah.
Okay, good. So that part where you pour water in the engine, right? It leads to the radiator. Now the radiator is somehow placed near the fan, okay, that runs when the engine is on. Okay, so the aim is that fan cools the water, okay, and then remember the radiator is designed in such a way that the water can flow from one point to the other. So if one part of the water is hot, right, the part that's closest to the fan,
You're doing some work.
the cooler. Do you get the concept?
Mm-hmm. Yeah.
Do you get the concept now?
Yeah.
Okay, so that's how convection happens in your car engine. Okay, so that's basically how convection happens. Remember, convection depends on actual movement of the water molecules or the gas molecules. Okay, so I think another concept of convection that you need to, where convection happens is sea breeze. Okay, so in the evenings, you've been to a beach before, right?
Mm-hmm.
So at times, you notice that air flows from over the water towards those who are on shore, at the beach. So that air that flows is cool air. Okay, it's usually, it moves because hot air which is lighter, has replaced it somehow above the water. So that's kind of creates a circular pattern, and that's how somehow those who are staying onshore on the beach, onshore at the beach, usually feel that cool breeze because the air that's directly above the water is cooler than the one that just, came to replace it. So it like moves in. So that's also convection. The concept of sea breeze I wish I had a diagram that would explain it, but well, let me see if there's any diagram to that effect here. But basically, those are the two basic concepts: convection in gases, convection in liquids. These ones are experiments, so I don't know if you can relate to them, but
Wait, can you go back up real
can
quick?
you
I was on
do
the last one, the one that
okay,
slide that
this
one.
one, the
No,
one
no,
I
the one you moved
okay,
from just now.
this one,
No, no, no.
okay, this one.
It's the one above.
Oh, okay, all right.
That one, yeah.
Okay, this one.
Yeah.
Okay,
I was on the last one.
okay, all right.
Hmm.
Just want to stop coming. No. Why do you think he's coming? It's me. Andrew, I would he really could be found third. If you know one could will have coming, but I let you use my love. We are on. It's not anything actually. No, it's not 6-7 at all. Last time it wasn't 6-7.
Wait, can you move like the
Adds up.
cursor
Even though it adds up.
from one?
Oh, sorry.
Yeah, thank you.
It does. And to feel like you touch, at least take out. I didn't take out from there every all the time. Leaving your friends. And I like. And what even leave it? Fine. Getting one in. No, wait, you shouldn't have that event.
Thank you.
Okay, you're good.
Thank you. Okay. Wait, can
All
I
right.
quickly go to the toilet? Can I quickly go?
Okay. If it's something that you could put, because anyway, I'm not sure how long my battery would last. But okay, so maybe we could continue on Monday. Okay, so at least we still have some
Okay.
time before the test.
Okay.
So yeah, we'll just do Monday evening. Um, so most likely, I hope I'm home by 6. But if not, I'll let you know if it's either 6:30 or
Okay.
7. We'll be having our Monday class. Okay. All right. So sorry, my battery is low. So but we'll
Uh,
continue. Yes. Okay. So just take a look at the notes again tonight. Then by Monday we'll continue.
okay. Okay.
Yeah.
Thank you.
All right. You're
Bye.
welcome. Yeah, bye.
Have a good night.